We're talking 99% of the time.
Right.
You can set up the other stuff, but now you're talking the multi-million-dollar equipment. If you go down to Home Depot, you're not getting stuff where you're gonna get protons being moved in the opposite direction. We need a symbol for current. So they went to the brain trust, and they thought, current, it's kind of like something that's flowing straight. What letter is straight? Oh, an I. So current, I'll put the serifs on it. But the symbol for current is I. Now, as the electrons flow, as the current flows, whichever way you want to look at it, it's going to run into things. The electrons are going to run into things, as we talked about before. It's not just moving straight. If it actually did move, the electron actually did just move straight, that's a superconductor. But our everyday experience, I don't know, is there superconducting medical equipment that any of you have dealt with? All right. So as the electron keeps bumping into stuff and is generating heat, it's losing some of that flow. Those electrons just aren't moving as fast as they could have because they keep running into things. Well, we need something to sort of measure what it's running into. It's the resistance, as it were. And so we come up with this thing called R, which stands for resistance. So we have Coulomb's law. I'll just do the magnitude of the electric force. Coulomb's law. And it can be derived, I'm not going to subject you to it, but it can be derived from here to the relationship between voltage, try that word again, voltage, current, and resistance. There's a relationship there. So, math and definitions. This becomes Ohm's law. Says that the voltage between 2 points is equal to the current times the resistance. The whole point of that was, one, that there is a relationship between the stuff we just talked about, but also the fact that it's just Coulomb's law disguised. Let's actually do a quick, simple problem there. I have a power supply. Now, before I drew a battery, we're getting slightly more sophisticated. This would be a DC power supply. For the purists, I know that it is a power cell, but for the purists, just deal with it. Technically, the power supply would be more than one of those things, and one of them is called a power cell. You need multiple power cells for it to be a whatever. I don't go for that. Although I have had some 252 students cringe because they were taught differently. So this is a DC power supply. So first off, DC, direct current. There's a D there. In direct current, the electrons will flow in pretty much, the drift velocity is always in one direction, or drift speed is always in the same general direction. As opposed to alternating current, where the electrons move one way, and then they move back, and they move one way, and the electrons just oscillate back and forth, hitting stuff as it goes. Our outlets, alternating current. Europe, direct current. Canada, I think, is alternating. It would make sense that they'd be the same as with us.
Why is it called DC when it should be DI if I equals current?
I had not thought about that because I'm so used to this, but yeah, because I think I is pretty international in terms of representing current. I don't know. A good friend, I mentioned her, oh no, that was a different class, Master Set. But good friend in college, Andrea, her middle name is Clarice, so her first two initials are AC. Her brother, David Clark, DC, their father was an electrical engineer. She claims that they named him that way on purpose for the AC/DC. But I should have asked him last time I saw them. All right, anyway. All right, so this is a circuit. I got the two sides here. One of them is positive, one of them is negative. And the way that I remember which is positive and negative is that if I make a plus sign, it takes twice as much ink as making a minus sign. So the one that takes more ink is the positive side, and the one that takes less ink is the negative side. Now, as the electrons, so the electrons are going to be coming out of this side over here. So my electrons will be traveling this way. My current is going to be traveling this way. Thanks, Ben Franklin. Now, as the electrons move, they're going to be hitting stuff. It's going to be generating some heat. They'll be encountering some resistance. So the way that they represent this is, well, in essence, the longer the wire is, the more resistance it's going to face. So imagine that you've got the long hallway right there, and you've got desks in there and various things. The longer the hallway is, the more chance you have to run into stuff. You're going to face more resistance. And so the representation of a resistor is, imagine you just got a really long wire crammed into a tiny little space. And so the resistor is that symbol, and that represents just a lot of wire. So that's the symbol for a resistor. And so typically what you would do in a circuit like that with resistance is you wouldn't go through and I wouldn't tell you how long the wire is, although I could, well, 152 and 252 I could. But what you would do is you would get your power supply, whatever that is, and then you would represent all the resistance as just a resistor in there. But this is my power supply with some voltage. It is DC because this is the symbol for a DC power supply, and there's my resistor. I have current flowing this way. The electrons flowing the other way. I know my voltage is equal to the current times resistance, so let's actually do some numbers. If this is a 12-volt battery, and my resistance is a 3-ohm resistor, well, I know that the voltage is equal to the current times resistance. So this is 12 volts is equal to my current times 3 ohms. The math problem is 12 is equal to 3x. That's the math problem. What is x? 4. So my current is 4. Well, I have a volt divided by an ohm. I divide both sides by 3 ohms. So that is a volt per ohm, which is definitely too much to write. Amps. And as was just said, that is an ampere. Named after, someone take a wild guess at who it was named after? Yeah, but with a French accent. Yeah. probably mangled it, and that's just the best I can do. This upside down, or sorry, not upside down, this omega right here, that the Greek letter is an omega. That's the Greek letter, and it represents an ohm. Ohm is the unit. Named after, yeah. Ashley.
What's the word you wrote connecting to A?
That?
Yeah.
Ampere. A-M-P-E-R-E. Now, if you want to shorten that, amps works. If you want to annoy me, where I have current there, the word is current. Some people like the word amperage. I do not accept amperage as a real word. So, to annoy me, and I've had some students do this deliberately. I know in everyday life, people use the word. Current is easier.
Is the answer 4A, or is it before, like, what answer would you take on a test, 4A or 4B over omega?
Either one.
Okay.
I probably would do A just because I know that if I'm dealing in ohms and volts, I'm gonna get amperes. Yes,
Is
then I,
that electrons on the left of
the electron's coming this way.
yeah, is that, what's that symbol? Where your hand is?
That right there,
Yes.
that's an I. Because the current's flowing, that would be counterclockwise in my circuit here. Yes,
Will you always provide the resistor number?
I could provide the current.
Oh, okay.
I mean, I need to provide some piece of information. In a 152 or 252 class, I could give you more information so you can derive this. You know, I can tell you the length of the wire, what the material is, and so forth. But for 110, no, unless there's a big groundswell for that. Ashlyn and Jason.
For the blue power supply, if the electrons are going that way, how come in the yellow power supply, how come the current is going the opposite way?
Because current goes the opposite direction of the electrons.
Mm.
Because they decided the direction of current before they knew what was actually moving. And it wasn't until the, let's say, late 1800s when they finally figured out that it was the electrons moving and not the protons.
Okay. And that's for, that's always.
Yeah, there are some books that will talk about electron current as opposed to traditional current, but
So
it's like
direct
apparent
current-
weight versus actual weight.
So direct current and electrical current are different.
So say it again.
Direct current and electrical current are different.
Direct current is a subset of electrical. AC and DC are both electrical currents. DC, the electrons are really traveling for the most part in one direction. AC, which is our system here, the electrons are moving back and forth like this, as opposed to in Europe where they move basically like this.
So say the first part again so I can write it down. The current goes opposite of the electrons.
So current travels opposite the direction of the electrons.
Okay. Thank you.
Okay. So I set my circuit again. I got my power supply. It doesn't always have to sort of point in that direction. It's just the way my mind's working right now. I got a resistor right here, and I got a resistor right here. Make that 12 volts. Make this 3 ohms, and make that 4 ohms. The question is, what is the current now? So if you think about, because the length of the wire is so important to what the resistance is. If I got a really long wire here, and I sort of think of it as two pieces, I got a piece here and a piece here. It's kind of like I got two resistors in a row. The official word, in series. I have two resistors in series. And so if I have current flowing across one resistor and it has no choice but to flow across the other resistor, they are in series. And if I think about it as terms of I've got a wire this long and a wire this long, well, that's pretty much the same as just having one wire the full length. So if I've got this series here, I can come up with what's an equivalent resistance. I can treat that as a single resistor of just, I only saw one hand, but I assume you had two fingers on the other hand. That's a 7 ohm resistor. So for resistors in series, you just add them. So this is the equivalent of, I've got 12 volt power supply, and I got a single resistor of 7 ohms, 12 volts. And so my current is my voltage divided by my resistance, which is 12 volts divided by 7 ohms.
1.714.
1.7 units.
Amps.
Volts per ohm for those who prefer that. So resistors in series, you just add.
So if you have resistors at the very beginning and the very end, it's still considered in the same series?
Yeah, because if I picture a current flowing across one of them, it has no choice but to flow across the other one.
Gotcha.
So far.
For the second one, if the 7 ohms was on the side, would it still be the same instead of on the top?
Oh, yes, yeah. Yeah, it really doesn't matter where in the wire that you put this in.
Okay.
Traditionally, you put it someplace where you got room. And recognize the 7 ohms here represents resistance throughout the entire wire. It's not like the current's going to be flowing along, you hit this and then suddenly slow down. It will slow down the current everywhere. So this 1.7 amp current is here, everywhere in the circuit. And if it's hooked up long enough, eventually the electrons leaving here will end up on the side of the battery. But when you first start, the electrons that end up on the positive side are the electrons from the wire itself. All right. Other questions to hear?
What does AC stand for?
Alternating current. There was the big fight in the 100-some years ago when they were trying to decide what the US was going to do, AC or DC. Edison, the big powerhouse, was trying to go for DC, because he had invested a great deal in DC. Westinghouse was putting his money behind AC, and so the electric wars began. So Edison tried to do whatever he could to discredit AC power. One of which was they started electrocuting animals using AC. And when people got given the death penalty, he made sure that they got killed with AC because he wanted to associate AC with death. The trouble is that over long distances, DC is not particularly efficient, was not at that time, not particularly efficient. So if you're sending stuff over 100 miles, there's a lot more loss if you're using DC than if you're using AC. And the person who came up with the device to allow that, to make AC much more what I'm looking for, efficient, thank you, was Tesla. Ashley?
You said AC is alternating current or circuit?
Current.
Current.
Did AC/DC really name themselves after that?
Yeah, I'm pretty sure they did. Is that a Y or a
Yeah.
wow?
Why?
It sounded cool to them? They realized they couldn't sing and they wanted to distract people from, any AC/DC fans in here? I'm glad that's over. Now, the symbol for AC circuit, because it's oscillating back and forth, the AC circuit, or the AC power supply, is basically a circle with a little wave in it. They indicate things oscillating back and forth.
Does
Here we go.
DC
Oh, no, Ashley.
Does DC have a symbol then?
Yeah, that's the symbol right here. That's DC. You got the short line, the long line. The mathematics that goes with AC circuits is similar to what we're doing here, but it's different enough that we are not going to do the math of AC circuits. Other than conceptually, we understand that things are moving back and forth. Voltage keeps flipping back and forth, current moves back and forth, etc. So now, I got my DC power supply. I have attached to it a 3 ohm resistor. I assume the wire doesn't have any resistance, because any resistance in the wire I'm bundling up into 3 ohms. Some textbooks will throw in an extra resistance as part of the power supply. If this is a 12-volt battery, we already talked about the fact that the current flowing through here would be 4 amperes. That was the problem that we had done. Yep, actually still up. Now what I'm going to do is I'm going to add a resistor to this. Got my 3 ohm resistor right there, got my 12-volt power supply, and what I'm going to do is I'm going to add a resistor there, and I'm going to make that 6 ohms. And the question is the current coming out of the power supply going to increase or decrease when I added that resistor, or stay the same?